Oh, okay, sure, sure. Take your time.
So you're going to sit here?
No, no. Nobody sitting there, you?
Yeah.
I'm sitting there.
All right, folks, welcome back.
Okay.
I hope you had a good lunch. Now I need your attention. All of you guys, please be seated and let's get started now. We have a packed schedule. All right, folks. So I really do need your attention because it turns out the paper says attention is all you need. Okay? This paper is foundational in the sense that a lot of the dominant architecture today, the transformer architecture, which underlies pretty much all the large language models, what we call LLMs, started with this work. This work dates back to the December 2017. The work was done a little bit earlier, but published. And when it came out, it solved a host of problems that people had in the domain of natural language processing. We'll talk about that. It solved it in such a resoundingly successful way that it is fair to say that in 2018, when people came back to the new year, they are the ones who are following through with all this. They knew the world had changed. Right after this came, in quick succession, another paper, BERT. Then came the paper GPT, then came the paper BERT. And these are things that have now practically become household names, at least in engineering halls. So we are going to cover this paper, Attention is All You Need, in quite some detail. I'll go over it carefully. I'll first give you a bit of a background before doing this paper, just enough natural language processing background, so you know what is the problem that this paper solves. Fair enough? Now, what people have, there is a concept of a language model. What is a language model? When people say large language model, what is language model? And is it recent work? It's been there for quite some time. So we'll see what a language model is. Imagine that you can give it a text. Well, this is too fat. Let me make this. The cow. Am I projecting or is it showing through? Cow jumped over the moon. Let's say, and I'll just add some of my own additions to it just to prove the point. Sure, joy. This is it. And I give you a task, some task, which is to say, what would it read like in, let's say, Hindi or French or Mandarin, a picture language? How would you translate that? Right? So you would agree that first what we need to do is take this text. Now, this text can exist in many languages, right? For example, in Hindi, or let's say in Tamil, I'll just put Hindi, guy, and so forth, right? And then there could be a French version, French, etc., etc. When you look at all these various texts and characters, the most intuitive thing that you derive from that is that they're all saying the same thing. They have to be. Otherwise, the word translation wouldn't have meaning, isn't it? It wouldn't be a fair translation. So there has to be, therefore, an underlying representation such that if I could produce that representation, right? If I could go from any bit of text to this, in some sense, the canonical representation of this statement, then I could from there forward engineer or decode in whichever language I pleased. Does that look logical, guys? Right? So once again, do you see the concept that in machine learning, we often search for hidden representations, the inner representations of things. So this I can decode into all of these ways thereafter. Not only decode as text, I may, for example, not just translation is an example. What else can you decode? A hidden representation. If I take text and I represent it in a particular way, take its essence, semantic essence, and I could capture it in a box, in a representation. Think wildly. What are some of the many things you can do with it? Besides just translation that comes to your mind.
Can draw pictures.
You can draw a picture of it potentially, yes. What else can I do? Summarize that. You could summarize, so let's do that. Depict. Translate is one. Depict, if you want. You could summarize. You could change the style of it. For example, you could say, now render it as Shakespeare's sonnet. Isn't it? Sonnets. Or you could say, for example, that my language is not so good. Could you rephrase it in a more formal or academic sounding language? For example, these days, it's become somewhat easier to write research papers because you can give it in colloquial language and the references, you can say, okay, clean it out into a more formal language, right? So you could do a style change.
Find similar sentences and other.
You could search for, yeah, I mean, you could take the representation and find which is the semantic array. But yeah, so you can see many, many things that you can do from this. You could convert it potentially downstream, feed it to something that can emit out an audio rendering of it, a voice rendering of it, right? Convert it to voice, convert it to picture, do many things. And maybe, and not just by this, but obviously by plugging in more pieces together, you see the beginnings of great things. Like, for example, you could generate images, videos, whatnot out of it. But you need, as a first step, you need to capture a true reflection, a representation of this text, isn't it? You could do that. You could do even more mundane things. You could do keyword extraction, for example. What exactly is it about? You could do question answer. For example, does it contain the answer to this question? You could ask, right? And I mean, all of those downstream things, some needing extra pieces to be added to this chain, but you need a hidden representation. That is your first step. So look at this journey. You take a text, you convert it into a hidden representation, you encode it. And from the encoding, then you decode it. Isn't it? To do that, this two-phase journey, to first create a hidden representation, a latent representation of text, and then to decode it, is to create a language model. So a language model is a pipeline of two pieces, an encoder and a decoder, right? Encoder will create a hidden representation and a decoder. And you can decode it to whatever you want. You give it a text. Are we together? Now, there is a problem, and it goes to the heart of this. How much space you give to the hidden representation. So, for example, sometimes, so even besides the technology that you use, it turns out that what amount of memory or capacity you give to the hidden representation, it's a theme that will carry through all of this workshop. It has implications, right? Because sometimes less is more. Those of you who are familiar with the autoencoder architecture, what happens is sometimes making it concise can be extracting or forcing the machine to extract the essence of things and throw away what is unessential, the noise. Right? We have all gone through this exercise in our life. Do you remember that you are in school, you all are given stories to read. Reading the story is fun. And then comes the dreadful part. Write it in 2 paragraphs. Summarize it, right? Basic writing and so forth, isn't it? What does it do? It forces you to take that which is essential and represent it. Now, one of the questions that somewhere along this line is important is, what is the optimal representation of anything? I can create representations. So one representation is I literally memorize the thing as it is and then move forward in some sense. But we'll do hidden representations. It's a topic that we'll cover. Now, before this paper came out and this transformer architecture that this paper introduced came out, the king of the hill in natural language processing, text processing, used to be something called recurrent neural networks, one particular neural architecture. We won't go over it too much, RNN. It stands for recurrent neural networks. Now, as I go forward, I'll keep throwing in or introducing you to some of the jargon in the field. One word that I will keep using is autoregressive. Does anybody have an idea what autoregressive is? Right? What it means is, you know what regression is? Right? Regression means you have an input, and based on the input, you make a prediction. So, for example, let's take the example of a young entrepreneur opening an ice cream shack on the beach. Right? So, if you're on the beach and you open an ice cream shop, the first thing that you'll observe is that, and the parameters of the game are that the young entrepreneur has to go get ice cream wholesale from a wholesaler, and in the morning set up the shop, sell ice cream. But if the ice creams remain, wholesaler is not going to take it back. Right? So it goes waste. So the young entrepreneur now has to just buy enough ice cream, not too little, not too much. And so it's a good prediction problem. Now, the young entrepreneur can say, hey, you know what? On warm days, more kids come, isn't it? So it becomes a predictor input. The other thing the entrepreneur may notice is that, young fellow may notice, she notices is that, oh, on days when it's a holiday, either because it's a weekend or it's a national holiday or something, more kids come, because who brings the kids? The parents bring the kids. They need to be free to bring them. That becomes another predictor for you. The third thing she may observe is that, oh, when it is windy and choppy, parents don't bring the kids. They fear bad high waves, right? And these days, I know rogue waves have become quite the fashion in California beaches. It's doing quite a bit of distraction, as you know. So all of these are input parameters: how windy it is, or how warm it is, temperature, whether it's a weekday or not. That's an input. But what is the variable that you're predicting? How much ice cream will I be able to sell today? That's what she's trying to figure out, isn't it? And therefore, that's a target variable, right? Input is your X vector input would be temperature, wind, day of week, or holiday or not, versus work day. Output is, in your prediction box, output is Y hat is ice cream sold. So if you build a prediction machine out of it, it's called a regression machine. You're building it out of temperature, wind, and holiday data, and how much ice cream sold, some historic data. Does it make sense? Right. So she's lucky because from somewhere she's managed to get that data to train her model on. Right. So the output and the input are entirely different things. Output is ice cream sold or expected to sell. Input is inputs are temperature, pressure, temperature, wind speed, and a holiday or not. That's a typical regression model. But they are a class of regression model where the input and output are very related. So, for example, if I were to, let's say that outside the temperature is, at this particular moment, I can tell you, in our beautiful California is 65 degrees, right? And sunny. Suppose I were to ask you to predict the weather in 10 minutes. What would you use it to predict? In the next 10 minutes, what's the weather going to be like?
Same, similar or same.
Yeah, you'll base it on what data? current weather and the weather that has been in the last few hours, isn't it? That would be a pretty good indicator. Temperature, you could just look at the temperature trend. You're predicting temperature based on past temperature, isn't it? When you predict something based on prior similar same variable, you're auto-regressing, means the target variable and the input variable are the same, isn't it? Do you see the meaning of it? Now, why does it take meaning in language models? I'm about to say. How did you know I was going to use the word say? Because I was about to. The words that I said a moment ago predicted the next logical word, say, isn't it? And so languages inherently are auto-regressive. Does it make sense? The next thing, the most logical word that you would say next is predicated upon the words that I have said so far. Therefore, the concept of auto-regressive. It's as simple as that. So it's a thing we learned, that languages are human conversations, natural language is auto-regressive, right? When it is not, you call it a non sequitur, or that's how you write it. I don't know what the exact pronunciation is. And anybody knows? Shruti, what's the correct pronunciation of the word non sequitur?
Non sequitur.
Literally, I'm saying it correctly. Good.
It's
Non-
actually
Non sequitur.
it's a non sequitur.
Non-sequitur.
Yeah.
Non sequitur.
Non sequitur. Thank you. Yeah, as an immigrant, I have no idea whether I'm saying something right or wrong. Right. I only see it in the written form. So, all right. So, autoregressive non sequiturs are rare. Usually, you can infer what's coming next. Now, with that as a backdrop, there used to be an architecture called RNN and its close cousins called LSTM and GRU. Right. I won't go into it. I'll club LSTMs because they are derivatives of RNN and GRU as just RNN. When I use the word RNN, it's a placeholder for that whole bag of tricks. So now, what is that bag of tricks? How does it work? That's a background to this. What used to happen is, when you have a sentence like this, the cow jumped over the moon, you would first go and feed it the word cow, right? So imagine that you have a box, magic box, right? This is your, literally a neural network, right? And you feed it the word the, and you expect it to produce two things, an output here and a hidden state. It could produce two things typically, hidden state. And what you do is, then you give it the next word. What's the next word? It is, let's say, this cow, the cow. Now, remember, this hidden state is based on what? Cow. Because that's the only word you have fed in. Right? You also feed in a little bit of a token. You say start. In the beginning, you feed it a start. You say the is the starting word. The and start together produces a hidden state called the cow. Are we together? And then what you do, oh no, sorry, not the cow. I apologize. The. And then the next word comes the cow. Is that correct? Next word is cow. So now this becomes cow. And what happens to the start? The word is not there. What you do is you take the hidden state, H, the hidden state produced by the word the, it goes into the box, and you don't give the start. From the bottom, you feed the last state of the machine, the last hidden state, latent state of the machine. You feed it back in, and you feed the next word. So what it will produce is some output, which you may or may not care about, and it will produce yet another hidden state, right? And you keep it feeding one word after the other. And soon it would have chomped through all of the words.
Question. So in this example,
Yeah.
so we have cow as the input,
right? Hidden state of the
No,
is
two inputs
Correct.
are there.
Cows
Cow
one and
and
two.
the hidden state of
state
the.
of the, and the output is H of the cow or cow.
Yeah, so the output that comes out now is made up of the cow. It is built out of the hidden state of the and the word cow. Both of these together synthesize to create a new hidden state. And you keep on doing it. So ultimately, what will happen? You will eventually get, as more and more jumped over the moon, you'll keep doing it. Finally, you will have the final hidden state, which has learned from all the words fed into it, isn't it? But by the time, let's look at the last word just for fun. To produce the last word, when you feed in joy, you are feeding in what? The hidden state coming from the rest, all the statement before it, H from everything before, right? To produce the output and the final hidden state, isn't it? So this final hidden state you call does it fulfill the need of this box? That in somehow it has been informed by all the words and their position in the sentence, right? And positions matter, right? And so one of the intricacies with language that has always been hard is in language everything matters. Even a dot or a comma matters. Any one of you who understand Hindi and Urdu, right? So if I may, I'll give you. I apologize for those of you who don't, but I'd like to entertain you with a bit of very amusing poetry in Urdu. It says, and let me see how many of you get it. नुक्ते की हेर फेर में खुदा जुदा हो जाता है. Anybody who got it? Nukta is a dot. If you misplace it, the Urdu word khuda, which is God, becomes zuda, means God. So you're parted from God if you just misplace a dot, right? So, and in English, there's a beautiful book that came out a long time ago. I find it very amusing. It says right? Eats, shoots, and leaves. What are we referring to?
Panda.
A panda, right? And now, this is fine, right? It looks like a cute panda. What happens if I put that looks like a murderous person, isn't it? Right? So does the value of even minor punctuation? And that's what makes language processing used to be extraordinarily hard for machine language. If you remember, just 5 years ago, if you really felt depressed someday, translate something in your language to some other language, and it would come out just hilarious, isn't it? Translations have been there for a very long time. They have never worked. Or do you remember speech recognition? Those of you who have tried speech recognition 5 years ago would remember that it was horrendous. You would pay a ton of money. There used to be, I remember that I had the misfortune of being gullible enough to buy in those days something called Dragon Naturally Speaking, right? Because my hands were tired from typing code, right? And I thought at least my emails I could do with Dragon Naturally Speaking. There was nothing natural about it. It produced gibberish, right? As far as our language is concerned. Pretty bad, actually. It's a work in progress. It's getting better, but much of the improvement that has come is because of the architecture that I'm going to tell you. I'll teach you about. Today, we have a sea change. These things really work. Yeah.
So the model that you just explained, Asif,
Yeah.
so that's not RNN. That is the attention is all we need.
No, I have not gotten to
The whole
attention
context.
at all. I have not.
Then what is this model that you just explained where we keep
This
building on
RNN?
the prior context?
Yeah, this is the RNN. Sorry, this is RNN. Let me just put
RNN.
RNN. Let me just put RNN family because LSTMs, etc., they all fall in this family. Go ahead.
So the RNN looks an awful lot like a mini state machine in logical design.
It is a state machine by all means. It is. It's just a very complicated state machine. It's not like your standard D latch or something. But yes, it's in the same family. Resonates with that. Right? Very much so. Now, so guys, now let's take away, because this is the background I wanted to give you. The takeaways are: do we know what a language model is? What is a language model made up of? An encoder and a decoder. Encoder produces in some sense, the true hidden mathematical representation of whatever has been said. Decoder then decodes it into whatever you want it to be. Right? That's a language model. The initial realizations of language models used to be with RNNs, where you would feed one word at a time, and it would lead to a hidden state, which would feedback, loop back. Therefore, the word autoregressive. You just keep feeding it back into the system.
The input of encoder is vector or text.
The text.
The input of encoder is
The
text,
text.
and encoder converts into vectors.
Into vectors. See, in reality, right, what you do is text, let me intuitively think text, but in reality, what you do is you take a dictionary, a finite dictionary, let's say of 30,000 words. One of them is a reserved words, none of the above, right? Because the human language has more than 30,000 words. And what you would do is you would just feed it the ID, the token ID. An ID for that. So there is more happening here, but let's stay at the level of the IDs.
What we were just talking, right? The input is both text as well as the hidden state.
The
that
hidden
happens
state.
to be the
hidden
vector.
state.
Right?
Exactly. But from outside, it looks as though you're feeding it one word at a time. Internally, this magic is happening. So what would happen, this kind of a machine used to have a problem, multiple problems. Two problems were, one was a real foundational problem. The hidden state would reflect more the recent words, and it would begin to forget or lose awareness of some of the earlier methods, earlier words. So for example, if you said the cow jumped over the moon, but suppose you said the cow who was grazing in the meadow all morning and had done giving milk, right? And later was playing with the kid, jumped over the moon. And by the end of it, it has no idea whether it is kid or the cow that jumped over the moon. Are we together? Right? It's too long. So the longer the text, the less it would remember the earlier parts of it, right? Because it has a finite transactional memory. And within it, it has to compress. So in other words, there's a recency bias, a bias towards remembering the tail end of the sentence, of the text. Are we together? So that was a foundational problem. There was another foundational problem. Another problem was a very practical problem. What was happening is that all these GPUs were coming out, and in the AI community, there were this computer vision guys, right? And they were having a really wonderful time because NVIDIA GPUs and other GPUs were coming. You could do ray tracing, you could do matrix multiplication, vectorization, and God knows what else. And suddenly there was ImageNet dataset, and benchmarks were being beaten, and ResNet was coming, and this was coming, and BGGNet was coming, and massive progress was happening, right? So AI, remember, as I mentioned to you, at least in the Tuesday session, walks on three legs: hardware, algorithms, and data. So the computer vision community was definitely benefiting from the data, right? Fei-Fei Li and all of these people were at Stanford were gathering this massive big data collection of images, right? They were benefiting from the hardware and algorithms, of course, mathematicians to the rescue. Great research was being done. They were galloping ahead. But look at the sorry state of the natural language processing world. They could not do any parallelization. It was just one unit, you had to feed it one word at a time, right? No matter what. And as you know, the CPUs, you don't really try to make them faster by increasing the clock speed. Clock speed, I think 6 gigahertz is pretty much the limit, isn't it? So all of these graphic cards, this AI, very powerful hardware, simply couldn't be used at all. There was no way to scale up. For example, if you want to translate half the world or all the world's knowledge into Hindi, and as you know, today, the governments are doing that. What they are doing is, now that translations are there, we are making all of human knowledge accessible in just about every language possible. The languages are called low resource languages, in which not enough literature is available. Today, you want to convert the entire Wikipedia into, let's take an example, into Gujarati, go ahead and do that, right? It will do it for you. So none of those were possible. So those were the key problems, forgetting part of it, and the fact that the whole thing was essentially a sequential machine, isn't it? And a sequential machine you can take only that far. And people, even the world was deep neural networks, but actually what people found is that going very deep wasn't helping it. By the way, I talked to you about the hidden state, the encoder part. What is the decoder part? How do you decode it? In the RNN world, the way you decode it is you have the hidden state and you pass it to another single unit and you give it a trigger word. You say, go at it. Something to the equivalent of go at it. It will produce the first word, right? Let's say it produced the word guy. Right, some word in Hindi word I put it, or whatever is the French of it and so forth, it would produce. And then what would you do? You would take, your hidden state is the hidden state, is there. You would take this word and feed it back in, whatever you produced, and it would produce the next word. Right? Guy, the.
Twice as slow.
What's that?
It was twice as slow. I guess.
Yeah, sort of. It was slow. So it would produce the next word. But you notice that autoregressive. You see the autoregressive thing baked into the system. These are very autoregressive things. It was doing its job. Now it was decoding. This is the decoding happening, isn't it? Because now you care. Remember, in the encoder, you didn't care much about the output. You didn't care about the output. You were just caring about the hidden state. In the decoder, you start observing the output because that's what you're looking at. Right? That's what you're accumulating. That's it. So that was the architecture. Its problems were there. And now let's read this paper. Okay. Attention is all you need. By now, you can see this paper has been revised. It is in B7 now.
So Asif, I have a question.
Yeah.
So in the decoder, you are giving
Yeah.
it the hidden state, right? The hidden state. So you have a sentence called "the cow is jumping." So it's not the hidden state of the or cow. It's a hidden state of the everything it completes. So
Absolutely.
right?
Yeah. It's the hidden state of the entire text that was fed in.
That text. So the output. So how come the output would be the guy? Output would be the everything in Hindi, right?
No, it produces one word at a time.
Oh, so even though if I give the whole hidden state, it gives one input and then it will feed
Yeah.
as input, then we get okay.
Next word, yeah. So that's the looping part of it, the sequential part of it. And now comes the fun part. This paper, I will read the abstract carefully, guys, because it matters. It says, and you notice that these are big guys. If you look at these names, these are all pretty big guys. This is Google Brain, Google Research, University of Toronto, right? These are all big research centers. And all of these guys now are big names, of course. Let's look at this. The dominant sequence transduction model. Models are based on complex recurrent or convolutional neural networks that include an encoder and decoder. Does this sentence make sense, guys? Sequential transduction model means something goes in, something else comes out. Right? Translation is an example of a transduction model. Are based on complex recurrent. I give you an example. You can do it with CNNs, but we won't talk about it. And they include an encoder and decoder. Does that sentence make total sense? Yeah. The best performing models also connect the encoder and decoder through an attention mechanism. This needs a little explanation. What happened is, there was an idea that came out in 2014 called attention. What that attention is, I'll explain. So people realized that if you took the word attention, you could get better results. You threw it into RNNs and hybridized it with attention concept, you would get better results. Now the question is, what is attention? But let's go through the history of it. Right. We propose a new simple network architecture, the transformer. Based solely on attention mechanism and dispensing with RNNs and convolution, recurrence and convolutions entirely. That is the crux of what they're saying. The rest of it is experimental results. It shows that it was amazing to do that. Right? So when the concept of attention came in, again, people didn't quite realize its full significance. RNNs were king of the hill. LSTMs, RNNs, GRUs were king of the hill. People had gotten so acclimatized to the fact that, of course, you have to use RNNs, LSTMs to do natural language processing, that any new idea was supposed to be an enhancement or an amplification of the performance of RNNs rather than a supplanting of it. Right? So I'll explain what the idea of attention is. It's a very intuitive and simple idea. Then it goes on to say experiments on 2 machine translation tasks show that these models to be superior in quality while being more parallelizable and requiring significantly less time. So what this part, in these 2 sentences, a lot is said. First, they are saying you can actually build a complete replacement of a transaction model, language model, using just attention. Therefore, the title, attention is all you need. And then comes the other crucial part of the statement. Experiments on 2 machine translations show that these models to be superior in quality while being more parallelizable. That's sort of the magic word that everybody was waiting for in a way. That's what makes you take notice. Like not only is it superior, but it removes a fundamental bottleneck.
If you don't mind, can you explain how?
Oh yes, that's what we'll do. Right? That's it. So hold on to that mystery. Hold on to that mystery. And trains in significantly less time. That's an understatement, actually. It just flattens the whole thing and makes massive parallelization possible. In fact, today, transformers are the biggest consumers of NVIDIA GPUs. Right? This particular architecture, if you want to know why NVIDIA has trillions of dollars of net worth, it starts with this. Right? So I will go into the rest of it. And they managed to train something very good in just 3.5 days on 8 GPUs. Whereas on a sequential model, you would go on training for days and days and days, and it would keep on forgetting some of the stuff, right? So, well, there we go. What is the model architecture? This picture has become iconic in our AI community, right? If you haven't seen this, if it is the first time, then I will go over this picture quite a bit, but if you Google it, it's probably the most, at this moment, iconic picture in the AI community. And so we'll go over this picture in very careful detail. It will also speak to one of you, I think, Shraddha, talking about word embeddings and their relevance in the new world, right? It will come to that. So suffice is to say, see, remember I said that encoders produce the hidden state. Decoders decode it, right? Decoders are auto-regressive, right? But the encoder actually need not be. One of the big insights here is encoder can take the whole text in one go. It need not derive its next hidden state from the previous state. In other words, no need for it to be auto-regressive. And which part is the encoder? Let me color it. This part is the encoder, right? This is your encoder. Which part is the decoder? Let's say this part is your decoder. But I'll let you stare at this picture. Do you see something interesting between the encoder and the decoder? Do you see any similarity? Yeah, they seem to have recycled the same parts, isn't it? But the same parts that you use for the encoder, they seem to have recycled for the decoder. And that's a good thing. In fact, that's a key insight. Right? Do you notice that there's something called multi-head attention? And then in this side, there is a multi-head attention of wearing a mask, right? So maybe it's COVID times. So it's a multi-head attention mask. Add a norma there. Embeddings are there. Feed forwards are there, right? So we'll talk about it. And it seems to have repeated itself. Now, there is also a magic thing called N5. So this architecture puts so many ideas together that in a way, this paper, actually, if we had to rewrite this paper, perhaps the authors would have spent a lot more time on the foundational ideas. But at that time, it was an architecture they created. And they noticed remarkably, you don't need RNNs or that whole family of things. And not only that, you can do parallelization. So this paper, I'll just scroll through it. you will see that it has only one real formula in it, attention, right? But I'll prefix this formula by saying it is not strictly attention, it is self-attention, right? I'll come to that in a bit. Then it just goes into benchmarks and technical details, right? And when you look at the technical details and how it does, you realize that it does right off the bat, it manages to either achieve the state of the art or beat it. Usually when new ideas come in research, they take some time to mature or even catch up with the state of the art of the previous technology, right? You give it some runway, but it off the gate began to beat the state of the art. Right? And there's a lot happening in this, but I will suffice is to say that it was doing extraordinarily well in all the benchmarks. These are the benchmarks, BLEO and so on and so forth. And I won't speak too much into it, but let me go up. Yeah. And if you notice that, I'll just read the conclusion and then I'll explain the paper in detail. In this work, we present the transformer, the first sequence transaction model based entirely on attention, replacing the recurrent layers. That's a crucial word, right? Most commonly used in encoder-decoder architectures with something called multi-head attention. The replacement unit is called multi-head attention, MHA. For translation tasks, the transformer can be trained significantly faster than architectures based on recurrent or combinational layers on both blah and blah and blah. We achieve a new state of the art. In the former task, our best model outperforms even all previously reported ensembles. Not only does it beat these architectures, but people would create assemblies of these and then do it. Right? Speaking of ensembles in the wisdom of crowds, did somebody find the average of the numbers posted on Slack? I need one volunteer to do that. Who is going to volunteer? All the guesses posted on Slack. Can somebody please find the average of it? Who volunteers? One hand, please. Okay, we do that. Jay is going to do that. And then we are going to count the stones. Right? So that will prove that wisdom of crowd works. It works for algorithms also. The best algorithms often are ensemble of other algorithms. So now, this paper needs a lot of unpacking to be done. I'll first start with the word attention. So now in this paper, they often mix up the word attention and self-attention. I'll be a little bit more precise and first speak of what is attention. And then I'll talk about what is self-attention. See guys, I go hiking in the morning, right? So I usually tend to go out when the stars are still shining. I get out of the house about 75 to 80 minutes before sunrise. So every day I see when the sunrise is going to be, and it's 75, 80 minutes. At that time, the stars are still out. And I take my hiking pole and I go on a lonely trail that takes me to the bay from my house. It's amazing that in Bay Area, where it's so crowded, but still you have lonely tracts of land, beautiful tracts of land. So as I'm walking, stars are shining, I'm enjoying. Then gradually the birds begin to chirp and the sunrise begins to happen and light comes and the fog over the river, over the creek begins to dissipate. And all sorts of interesting things happen that I enjoy. But occasionally, very rarely, suddenly I'll hear, wow. Do you think I'm enjoying the scenery anymore? What has happened? I'm suddenly on the watch out. Is it a coyote? Is it a coyote or a mountain lion? Where is it? Isn't it? So your attention immediately goes only to the bushes, to the little bushes growing next to the path, isn't it? So it has gotten a context. There is a context. The context is wow. And it has focused my attention to just one place. I'm looking for that hiding mountain lion or that coyote, isn't it? You see that, right? So it got focused. That is attention. Attention is that given a collection of things that you could equally attentive. So when I'm taking a nature walk, hike in the morning, I'm enjoying everything. I'm enjoying the sky. I'm enjoying the fog on the river, on the creek, right? I'm enjoying the birds chirping. It is all within getting more or less equal attention, right? But the moment I hear that sound, that becomes a new context. That forces everything disappears. I have no idea how the sky looks anymore at that moment, right? We are scanning, where is that? Where is it? That selective, giving differential focus or attention to different pieces of the input is the technical definition of attention. Are we together? Right? Now let's bring it down to a bit more technical detail. Suppose you are the classifier between a human face and let's take something else. Let's take cars.
Male versus female.
Come again?
Male versus female. Classified.
Male versus female. No, that's a sensitive topic. I'll stay away from that. Yeah. So a human face versus a car. Right. So suppose I give you a lot of pictures, and those pictures have a kid, and she's sitting upon a boat, right? And there's a tree growing in the background. And you ask, just intuitively, I ask, is it a picture of do you see a child or do you see a car there? You would say, what would help you determine it? Is it the boat? Cars can ride boats. Is it the tree? There can be tree in the background of a car. What made you tell the kid is a kid? Which part was really the key point? The face, right? And so you paid overwhelming importance when you have to discriminate between a face and a car, person in a car, you pay disproportionate attention to the face. And all of you dog owners know that, right? Dogs have a very keen eye for your face. Right? They actually can tell when you are smiling and when you are pretending to smile. Right? Most humans can't, apparently. So this is the face. So this is attention. In this picture, you're paying attention to this much more. Do you get the concept of attention? Right? So I'll give you, now let's try to make it even more technical. Suppose I gave you a bunch of numbers, a sequence of numbers, right? So I gave you number N1, Nk as input, right? I give it to you as an input to a box. And I ask you, tell me which is the biggest number, right? So you could do that. What you could do is you could take a traditional neural network, a feed-forward network, feed-forward network, sir? Just the typical picture of a neural network. Lots of neurons propagating information to the next layer, to the next layer. What has existed since eternity, right? You would feed it in, and then you would have a predictor. It would tell which of the numbers is the biggest number, right? And it would come out with an answer, and it would have some way of learning which input to give emphasis to, right? Somehow it would do that. But what if you could do this? Now comes the interesting thing. What if this machine could somehow have a sense of context? Let's say, just something like, I'll take an example. What if it could figure out what the average is? A very simple context. It knows what the average of the numbers is, right? And then it compared every number to the average and looked at how far from the average it is, in the positive or the negative direction. And then finding the max is easy, right? Relatively speaking. It's a very trivial example and not terribly useful, but think of it like that. You can extract a context vector that tells you the global state of the number, right? So then what you could do is based on the global state, you could then pay more attention to numbers, surely, which are more than the average, than the numbers that are less than the average. Does that make sense? When you're searching for the max? So attention, and this word importantly, it needs a context with reference to which you decide how much attention to give to each numbers. And let us say that ideally, let us say that the numbers this was the biggest number, 101, and all numbers were small. What you want is just like this baby's face, child's face. You want it to light up. So what you want to do is, in reference to the context, you want it to, or it needs to sort of somehow light up most. Are we together? Light up most. So you can say, that's it. Right? That's the concept of attention.
So how do you make something like that? Is it a specific vector?
Yeah. So we'll go through the math. So attention in itself, to work out the full details, we will do it in the Tuesday class. But here I'm just giving you a big flavor of it, because remember, this is not so theoretical. It's about do. But I'll cover this paper. I'll give you partly the answer. The rest, Tuesday, I think you're coming, right? So you'll get it later. So that's the concept of attention. Now, what these researchers said is that, see, look, suppose I got the word, the cow jumped over the moon. Or let's take the example they mentioned in the paper. In the appendix, they mention a sentence like, the law will never be perfect, but its application should be just. This is what we are missing, in my opinion. It's a pretty long sentence, right? Now, you know that if you're going to translate it into French, let's say, I think that's what they think, or something like that, then the order of the French words would not be the same as the order of the English words, isn't it? But how would you emit out the right words is the question. So the concept here that they employ is of attention. They create this thing. They say that suppose every word knows how much attention to pay to all the other words
In the sentence, right?
in the sentence. You give it input. Every word, let's say that the words are word. So first of all, so here's the thing. You give it the word. Let's go over a cow. I like cows. So the cow jumped over the moon. I meet a lot of them in my morning walk. The cow jumped over the moon. Right? Now, the cow, when you're translating this, if you think about it, jumped and moon are the words probably are most relevant to it in the sentence, isn't it? Make sense, guys? And likewise, moon might want to pay a lot of attention to the cow. So this is attention. Every word needs to determine how much attention it pays to the other words. Right. Now, how is this attention computed? The way it's done is quite interesting. And this is called self-attention, actually. Strictly speaking, this paper introduces the concept of self-attention, because attention was introduced longer, 3-4 years ago, prior to this work, by another paper from Google in 2014.
This is called self-attentions?
Because the words in the sentence are paying attention to each other.
So this is, in your example, using from the perspective of cow.
No, from the perspective of the sentence. That the sentence is in a way introspective.
Without any supervision.
Without anything other context. Right? So, and you feed now here's the beautiful thing. So let's go back to the thing that should have run it. What do we do with words? First thing we can do is, step by step we have to go through. You have a dictionary. A dictionary, right? A table of, let's say, 30K words, which is quite common. Unless you have Google, then you might have a dictionary of 1 million words or something. But let's take 30K, it's common. For every word from aardvark to Zephyr, you list it in alphabetical order. So now for each word, you know its index, its location, right? 0, 1. Its location. It's its ID. Right? And then you throw in the digits also and question mark and everything. Everything has a place. That's why you don't use the word in natural language processing. You tend to use a generalization of word. You call it a token. A token could be a word, a question mark, a punctuation, a number, anything. It's a token. Token is the generalization of word.
And sentence, a bunch of tokens.
And a sentence is a bunch of tokens, exactly. It's a bunch of tokens, punctuations and all, right? So, and a token must belong to a dictionary, a vocabulary. Actually, the word people use is not dictionary. They use, the technical word is vocabulary. So, vocabulary of 30K words. And if it isn't one of those words, just throw it into the remainder bin. Create a token called God knows. Put it there. Right? And you're done. Right? Now what you do is, this technology of word embeddings existed. You could convert this into a vector. Convert it into a vector. Right? So whenever you get a word, so a word gets to embedding, and associated with each of them, let's say there is a word vector, EI, an embedding vector. Whatever dimension, 300 dimension or whatever it is, it's your embedding vector. So that you take as an input. Then here is what you do in the box. You take this word and pay attention. So now I will use the word EI for the embedding, word embedding. Think of it as a unique vector associated with every word in the vocabulary, right? Word embedding, and these things, for example, can belong to a 300 dimensional space, potentially. Yeah. And that technology has been there for a while. The first paper came out in, I believe Word2Vec came out in 2014. Somebody correct me if you remember the exact date. Now, you will end up with the cow jumped over the moon. You will end up with an embedding for each one of them. Let me call it E0, E1, E2, E3, E4, E5, and then there's a full stop, so E6. Make sense, guys? Right. So you ended up with 7 tokens. 7 tokens and then 7 embedding vectors. Then what you do is you take a box and you say, in this box, you plan to do this. In this box, you need to push these guys in, E1, E0 all the way to E7. E6, right? 7 vectors. You feed it in. Now, at the same time, but when you do it, your first reaction, if you come from the RNN world, is, now wait a minute. You can't just shove all of them in at the same time. Why? How would we know which came first and which came second? Isn't it? So there is a problem. So then what you do is you say, okay, no, it's not that bad. What we'll do is we will attach to it one more vector, which is declares its position, E0, will append to it, like concatenate with it, a vector, which is a position vector, E6. Now, there's a bit of a simple technical argument. I'll let you discover it. Why you can't just introduce the word 0, 1, 2, 3, 4, 5, 6 as vectors and append to it, the numbers is appended. You can't do that, actually. Because if you do that, then the last word is, you're basically giving it more actual value. You're giving it 6. You don't do that. You want to keep a normalized vector, balanced out vector there. So you concatenate a position vector. Now, how do you manufacture that? This paper, by the way, is now considered a classic in its field, right? This is like ancient history. They used a technique based on trigonometric functions, but today we don't do that. Even the position vectors, we let the neural network self-discover, learn it, right? But that gets, that's why I'm not going to go into the technical details of the position vector, because let's focus on things that have lived. So you do that. So now what happens is, so let's go back to the picture. We understood some part of it. Oh, what did we understand? Look at this. Input goes in, input becomes input embedding. These are your word embeddings, right? Each of them. And so all the 7 word vectors. Now you're concatenating it with what? The position encoding, position vectors. So then they become the final vector for each word, each token. And you have 7 tokens. The cow jumped over the moon, full stop.
7 encoded vectors,
Yeah,
concatenated with.
a position vector for each of them. So you have 7 vectors, long vectors, which tell the word and their position. And then you feed it into this funny box called attention box, attention head. Now, what is an attention head? We'll talk about that.
What's called attention?
Head. People have used this word, attention. What does it do? It does something actually quite interesting, and that needs a little bit, that's what the next picture is about. Actually, this doesn't have that picture, so let me explain what it does. What you do is, you take the vector, let me just take that total vector, I'll just use the word V, right? V is embedding, VI is embedding with the position. Can I create a little vocabulary, VI as a vector for each of the words? So you take VI, and what you do is, you multiply it, a vector. Now, a little bit of, very simple bit of linear algebra. See, there is a field of mathematics called linear algebra. We have all done it in one of our past lives. Right? So what does it do? Linear algebra is a study of linear transformations of vectors. What it means is, a vector is nothing but a point in a page, if you are thinking 2-dimensional. So you're saying that if that point walks across and moves somewhere else, right, you can describe that movement. Right? So here's the thing. Suppose this is the gist of linear algebra. Suppose I have a point here, x, and you have a point there, x tilde. And you suspect, you ask this question, how can x go here? Right? Then you say, wait a minute, and I allow you only 3 operations. I allow you to stretch or shrink, opposite of stretching, scale. I allow you to scale, I allow you to rotate, and I allow you to reflect. Right? In other words, this thing along this is minus x, right? Which is a form of scaling in a way. So let's just say you can stretch, shrink, and a funny kind in which you just reflect it in the opposite direction, or you can rotate. Now, how can x using only these 2 operations become x tilde? And so you say, well, that's easy. All I need to do is rotate it in this direction, rotate it by this angle theta, and then stretch it. You see that, right? So there is you just need a matrix, right? A, B, C, D. If you just multiply the location of this, let's say that this was xy, with this, every matrix does a little bit of a stretching and a little bit of a rotation. Are we together? Some matrices may choose to do only rotation and no stretching, right? That is stretching by 1, multiplying it, scaling it just by 1. But rotation, those are called rotation matrices. Some matrices just do scaling. They're called stretching matrices, right? But this is what matrices do. Do you get the intuition of a matrix? Right? That's all it is, guys. Linear algebra is like, if a point hops from here to there, who is the culprit? The culprit is a matrix. That matrix did the job of taking it from here to there. That's why the word linear comes in linear algebra, comes from that, because both of these operations are, if in a more formal term, these are called linear transformations for a mathematical reason, right? So stretching, scaling, and rotations, matrices do. Those are the simplest things you can do. The important word is, whenever you do a transformation of something linearly, you don't tamper with it much. Let's say I take this page. Oh, I need to take a page. Okay. Let me take an independent page. Okay. You take this page. I can't stretch it, but if I rotate it, is the page still the page? It's the, so imagine this data is this page, all the points on this page. I'm rotating, I can flip it, I can do all sorts of things. Even if I stretch it a little bit, it would still contain exactly the same thing. But what happens if I do this? Now, can you read it? No. Right? So in other words, I can do nonlinear transformations on it. And I can do linear rotations and stretching, simple ones. Now, here is a fact I'll just lay on the table because the context of the Tuesday thing. Neural networks are engines that do two things only, right, successively. At heart, I mean, a simple feed-forward, let's take a simple feed-forward network. It's true for other things also, but I'll come to that. Neural networks and these things, they are engines that do a linear transformation. Are we together? Followed by a nonlinear transformation. Right? Nonlinear transformation, easiest way to think of a nonlinear transformation is elastic band or something. Like, you know, when you take dough, okay, let me give you a very practical example. Cup, I don't have a cup here. Suppose I were to tell you the cup is the same as a donut. How is that possible? Mathematicians would all agree, so of course. How is that possible? You don't eat cups or sip from donuts. Right? How is that possible? Why is a cup the same as a donut and all mathematicians agree? Geometrically, yes. Why are they the same? Think about it this way. Imagine a donut.
Donut can become a cup.
Yeah, right. I hope I've gotten a donut. Yeah. Then in the donut, imagine it's made up of Play-Doh. You start pinching this corner out and pinch and pinch and pinch this. What has it become? A cup. You can do it with slow, continuous deformations, right? Very slow deformations. Those are called, there's a technical term for it. These are called homeomorphisms. Homeomorphisms are slow, continuous deformations. So very slowly, imperceptibly, you can change a cup to a donut, isn't it? Does that make sense? But it's a very nonlinear. There's no way you can do it just by rotations and stretching. So those are nonlinear transformations. So in a neural network, and I'll just give you a very simple primer. See what happens is, look at a neuron. Suppose you have inputs coming in, x1, x2, x3, w1, w2, w3. What do you get? You get a z, which is up to a bias term, w0. It is just x1, w1 plus x2, w2 plus x3, w3. Isn't it? One way to think of it is using a very electrical analogy, right? Imagine that x1, x2, x3 are, what should we say? Let's say they're currents coming in, right? And weights are the, you guys know something called a rheostat, right? Variable resistance, right? So these are variable resistance. You could slide it back and forth and decide how much voltage will go across by changing the resistance of the wire, right? Or how much things will pass through. Or if you think of it as a voltage, as how much current will go through and so forth, right? So the net result is, the end result will be something like this, additive property, right? So that's one way of doing it. So whenever you think of weights, at some sense, and this is one intuition I'll give you from my experience, may or may not work for you. Whenever you get all these funny symbols on the page, and people just matter of fact walk over it, don't do that. Pause, relate it to something real in life, something tangible you have held and smelt and maybe got electrical shock out of, right? Then it's very tangible. You won't forget it. So I think of weights as the rheostats, right? From your engineering classes. You can change. And all that the neural networks do is they find the best position of the rheostats, you know, the things. So then what happens is, there you have an activation function that you apply, which is a nonlinear function. It will distort it. Whatever input you get, it will distort it. So neural networks are nothing but linear transformations followed by deformations. And that's why I often say that you should think of them as deformation engines. is a deformation mode. So we'll hold that thought. Now, why did I go across this digression? Here comes. Do I hear somebody remote say something?
A question, Asif. You had the analogy of linear algebra to the matrix, right? How is the point change as converted to a matrix? I didn't understand that.
Oh, what happens is that you take a point. Let's say that I'll take a point, this point.
Mhm.
This point is unit 2 along the x-axis, and
Correct.
let's say unit 3. So it is 2, 3. The
Mhm.
xy is
Correct.
equal to. Take any matrix. Take a matrix like 1, 2, 3, 4.
Mhm.
Or right, and multiply it by this. You will
Mhm.
see that this becomes, what does it become? 8, and 3 times 2 is 6 times 12, 18. It becomes 18, right? So this point now becomes 8, 18. 8,
Mhm.
18 is somewhere here. Well, it has become a huge number. It has become something here, right? So this vector has become this vector.
Okay.
Right?
Okay. Now
That
I
is it.
understand.
And you can think of it as partly rotation. First, you align the direction, and then you stretch it. Isn't
Got it.
Then you stretch it. That's all that linear algebra is, right? So, so now you wonder why that course was so hard in college.
So, the name of the paper or the model transformers.
Yeah.
Because we are transforming. It's called transformer. Is there any connection between those two things?
See, transformers. Why did they choose the word transformers? Engineers pick up good words, and all engineers are kids who watch transformer movies. Right? So, but more seriously, see, it's a transduction engine. It's an encoder decoder engine. It does transform input to sum.
Yeah, that's why. So because like
Maybe
mathematically it is transforming. So
Yeah.
that
That is right. Transformers. They were looking for a word in the text. Right? So, all right, guys. So now what happens is, now here's the part that you need to pay attention to. So I take a word, a vector, which is made up of what? It is internally made up of EI and a position encoding, right? And what you do is you multiply it with one matrix. So what will it do? It will and you project it. In this paper, they project it in a 64-dimensional space. But it doesn't matter. I'll just take a k-dimension space. Right? You project this into a 64-dimension. Actually, it's in a form dimensionality reduction because they're going from 300 to 64. You do this. If I multiply, I will get a vector in ki in 64 dimensions, isn't it? If I multiply this with vi, I will get this. Take a fixed matrix, right? And do that, rectangular matrix. And then you bring in one more matrix, completely different. You call it VQ. And here's the thing. They had the idea of bringing in 3 matrices, KQV. Why those words? Because they're Google. And what does Google do? Search, right? What is search about? Querying. They use querying. And when you query, the easiest query you can do, if you're doing inverted index, for example, is query into a hash table where there are keys and values. Right? So a lot of the picture, I'm just guessing that a lot of the mindset or the frame that they have, it is so much induced by information retrieval thinking that it came very natural to them. And they said, what if we could take this vector, break it out into VI, QI, and VI. Oh, I shouldn't have used the word V. So let me just use the word WI here. This is the value. They call it the key query value. And here is the interpretation they give. See, in a hash table, what is a key? A key is the location, right, in the hash table, where the value is stored. Right? The value is the main thing, but key is the address. Right? And query is your whatever you're querying for. So the intuition they brought to this was delightful, actually. It's very nice. They say that, and again, by the way, there are many other alternatives. For example, people have tried to come up with a formulation of attention without this formalism, KQV formalism. A lot of people, a lot of very serious scientists believe that there is something deeper going on here. And so we need to have a different formulation of what really is going on. Yeah. But this is the formulation they started out with. They say that every word has a certain value, right? So there's a V of a cow, value of a cow. So there's a value vector in this R64 dimensional space, or more generally, K dimensional space, right? By the way, when I write then R with an unnecessary extra line, what does that stand for?
Space.
Euclidean space, a flat Euclidean space, right? In which Euclidean distances and all that we consider common sense holds, right? Then that cow word's location is the key. Are we together? Location is the key. And now what happens is, if we want to find out how much attention, if we position the location properly, it is somewhat like the search. Given a search query, we just have to see what word it maps to. But in a search, it is an exact match, right? When you're looking through a hash table, you better know you have a key's exact match. But now let's go into the probabilistic domain, right? Because machine learning is all probabilistic. What if the word that you are given, the query word, sort of most aligns with which of the keys, and therefore vector algebra, right? Vector spaces, because you can look at how aligned two words are in a space. How do you look how aligned two words are in a space? Anybody remember something in dot product, right? Two vectors which are perfectly aligned, if they're unit vectors, the dot product would be 1, isn't it? If they're oppositely aligned, right, then their dot product would be -1. And if they are orthogonal to each other, their dot product would be 0, right? If they're unit vectors. And now you generalize from it. You can add numbers, so positive numbers. So what they say is that given two vectors, key, like suppose you get a query, a word, the cow needs to figure out which word should I pay attention to. The cow jumped over the moon. So this is a statement. The cow jumped over the moon. Enjoy. Let's say. I added that one. The cow. Which word? So what it will do is, it is holding a torchlight. It's a query vector, because it itself burst out into a query and a key and a value. But when it is asking who should I pay attention to, what matters for the cow is its query vector. Are we together? It will take its query vector and see, hey, query vector of the cow is here. The query vector. Query vector of the cow is here. It will ask which vectors are aligned with me, right? And what will happen is, magically, or rather through the mechanisms of neural networks, it may so turn out that the moon's key vector is nearby. Key of the moon is nearby, right? And so it is far more aligned to moon than it is aligned, for example, to the word over. The key of the over, right? So it is.
So that's.
I'll come to questions, guys. Let me finish this thought. So if the key query is searching for the keys, very much like looking in a hash table. Query is searching for the keys. What am I aligned to? And the way you do that is you say k.q cow query cow. It looks for its alignment to every other word, isn't it? Every other word I in the sentence. And based on how much it is aligned, because you realize that dot product is alignment. By the way, I tend to write dot products like this. It is my notation. Angle bracket. It's called bracket sort of notation. Then I say that is my measure of attention. And pay attention to what I'm saying. Attention that cow pays to ith word. This is the attention that cow pays to the ith word. Are we making sense? Right. It is the attention score, And then you multiply it by the value. So let me just call it the A cow, sort of, little bit, attention score, actually score cow, score that cow has towards the word I. And if you want to know what is the full attention cow pays to the ith word, it is this alignment Q cow with the key multiplied by the value of that word, VI. Do you see that? Does it make intuitive sense now? Right? I said, first figure out, okay, how much? A little bit to this guy. And how much is the value of this guy? Okay, this much. Yeah? So multiply the score with the value of that word, with that token. So this is it. Now, there is a technical detail, by the way. What you do is, when you pay attention, and it's sort of a mechanical thing, you also square root it with D. But here is a point. When you do this attention business, you don't want to pay, you don't just do dot product. You do something like, you want to divide a unit attention amongst the different words. Like, suppose I give you my score of attention for you is 0.6 and for you is 0.3. How much am I left with? 0.1, right? So I need to. So there is a trick. And this is again a mathematical trick. If I softmax, there's a function called softmax, right? It will take any bunch of numbers, positive or negative, and it will create another bunch of numbers such that they add up to 1, right? Softmax is it's the simplest mathematical trick to convert a bunch of numbers to proportions or probabilities, right? Interchangeably. Are we together? So therefore, the key, the heart of the thing is this: Q cow, KI, and VI, right? Then let me use a lesser color. Some things are technical details, like, for example, mathematical details, which is that I can do, for reasons, it turns out that making square root, dividing it, 64 square root is 8. Dividing it by 8, it turns out, is a good idea for computational reasons. It has no theoretical meaning in itself, right? So you don't like it, you can put your own number and try what happens, right? And then, because we want to distribute it to a total of 1, it's again a implementation detail, softmax it. Are we together?
I said, what was root B here?
B is the dimension, the number of dimensions of the target space, 64.
Okay, okay.
D is the dimensionality of the target space.
For a moment, I got confused with distance, then I realized you said 64, so.
Right, dimensionality of the target space.
This is for this sentence.
1 second. Go ahead.
So, I lost just one part. Which
Yeah.
is, how do you arrive at the score? The Q, cow.
Yeah, I'll repeat that. It's an important part.
Come up the score. That part I missed.
Okay. See, what I'm saying is, imagine that you are writing, you're looking in typical programming, right? You store things into a hash table. How do you store it? It's a locker room. See, here's the thing. You have a locker room at the airport or somewhere. What do? You give your thing, your suitcase, you get a key. That key has a number. It's locker number this. You have it. You walk away with it. And now a customer comes and says, okay, I want my stuff. Right? I need to get my stuff, and gives you a number. That number better match a key that you have. If it doesn't, there's nothing there. Right? So the query, when he comes back with it, in effect, what the token that you give him is the query. He has to come back with it. That query has to match the number written on the locker room door. That's the key, isn't it? And if the token matches that door's number, the key, then you will open that particular locker and give him the stuff. That is the concept of a hash table. Please, well, let me finish the argument. So that is the concept of a hash table. So far, so good?
Yeah.
That's how hash tables are in computer. Now let's generalize it a little bit to search. Suppose you don't need exact matches. Close enough is good enough. How would you do it? When close enough is good enough, you need a notion of closeness. Somebody comes up with a key, it's almost like, that you gave them a token, and token you have erased it, and some of the digits are, it's been wet in the rain. All right. And this guy comes and you see, what is this? Maybe 61 or something. You will look for the closest match on the door, right? How would you do that? Well, in mathematics, you look for dot product between two vectors. Right? So that explains the dot product. That explains this dot product to you.
One is the query, other is the key.
That is right.
The query cow, is it a vector?
Yeah, it's a
Key
vector.
It's a key vector? No, it's a key vector of the query.
Yes. So no. Okay,
so-
let's go back again, guys.
Yeah.
See, here's the thing. Each of these words, and pay attention, each of these words, after all, we are understanding attention. So each of these words develops its own query key and value, right? So now cow has a query vector, and every other word also has a query vector, which cow doesn't care about. But cow cares about the key and the value vector of all the other words, right? So the question is, cow is swishing its tail and wondering, how much attention do I need to pay to each of the words? It's a puzzle. And how would it answer the puzzle? Very much like looking through a hash table, probabilistic kind of a hash table. It will say, hey, I have this token, I have this query, cow query. I can now look for which key it aligns with, which word's key it aligns with most, or how much it aligns with each. And that becomes, that alignment is the score. It is, that's the word, is attention score. So let me write those words down.
How did we align
One second.
cow and moon?
What's that?
To be close to each other?
Oh,
Already
at
taken
this
for
moment, I
granted,
just
yeah.
said there's a magic fairy that put its wand and everything fell in the right place. Just assume for now. So the how part is backdrop. For that, you come to Tuesday. Right? But hang on, guys. Let me answer one person. So all I'm saying is, let us say that magically, all the right words, right, they just burst out into their right places. How it happened, we'll worry about it. It's actually, there's no mystery to it. It's just gradient descent backdrop. Right? But how and why that algorithm is so amazingly effective is a topic in its own right. But let's keep that. All we know is we have a concept of attention score that cow pays to word I. This is the question. This big expression is given by, what is it given by? The query cow with its dot product with the ith word, This is the score, the degree of attention that it will pay. But now comes the thing, just for technical reasons, you can ignore this square root of d. It's just there. Remember, see guys, in theoretical physics, there was a very simple rule. When I went, at one point, I took a digression away from engineering and decided it was a good idea between my two different engineering degrees to go and do doctoral work in theoretical physics, quantum field theory. So when I went there, I noticed that these scientists were doing something strange. Right? These are big heads, Nobel laureates, but they would write things like E is equal to M. And I used to say, what about C square? Right? Isn't the popular imagination E is equal to MC square? What happened to C square? And they would say, no. We just set the speed of light equal to 1. You're right. So it goes away. So it's more, but if you think about it, it's just more intuitive because energy and mass are the same thing in their way of thinking, right? So in the same way, I am the kind of person, there is a square root of d, but I choose not to see it. That's why I put it in a different color. Pay attention to the concept. This is the score. Now I ask this question, but this score can be a number, arbitrary number. What I want to know is differentially how much attention this cow needs to pay to this, to this, to this, to this, right? So what I want the scores to be adding up to 1, right? So what is the trick to do that? Normalize it. So let me use the word normalize it, if I may, it with softmax. I mean, I know some people will cringe if I use the word normalize, but for me, just go along with it, right? Or standardize or whatever it is, balance it out. something like that. Softmax is the trick. Softmax is a lovely function, cow, Ki, square root of D. Right? You take this. So what will come out? A score between cow and I will come out. A joint score, how much attention cow, how much score it gives, cow gives to the ith word will come. Right? So guys, do you remember, even though I put softmax there, square root of D, all I'm looking for is the alignment between the query and the key. That's it. That's the heart of it. And now comes the attention vector. The total attention.
So why are you
Hold
saying?
your question, guys. I know that many people in the audience have questions. Just hold all your questions. Attention. What is the attention that cow pays? Because cow is paying attention not just to this word, but to all the other words, right? It has a score for every other word. Right? It is nothing but the score of the cow with respect to the ith word times the vector I. Right? You sum over all the I vectors, and what it will do is it will pay attention towards something. And usually, maybe the cow will be pointing much more towards moon than towards other things. Are we together? It will have more score towards attention. And before you, I will take those attention. And so what happens is, if I write this in all its glory, it becomes this thing, softmax cow, Ki, square root of D, Vi, right? And this is for the cow, attention cow is equal to this, right? This equation. And now if you take what is the total attention vector matrix for each word to every other word, like everything else, that then becomes this very compact equation, which first time you look at it, unless you're very familiar with the mathematics of things, you have no idea exactly how did they pull this out of their hat, right? But now does it make total sense? Right? Look at this, guys. I'll just expand it. Now, is this what I have been saying? Yeah. Okay. So lots of questions. Let me take the one on the Zoom first. Somebody was asking a question on Zoom. Please go ahead.
I think you explained. I was asking that why you were saying ith word, but you did the summation I equal to 1 to n. So I understood that.
Okay. Okay. What other questions are here in the audience? We'll take it. Go ahead. Guys, please don't take a break. I'm just finishing. Oh.
Let's say you have 33,000 words.
Yeah.
Right. So on your query of one word.
No, I'm just taking one sentence, Grover. At this moment, how much attention one word within the sentence is paying to the other words? That's it. Yeah. So so there is an author in Britain, used to be, named Francis Bacon. And he would start his sentences notoriously. If you would turn the page, it would start from the top left, right? Fill the entire page, and then fill the next page and end at the end of the next page. And that would be one sentence.
The goal of this is to predict the next word.
No, I never spoke about any goals. I'm just bringing in a technology. I'm saying attention. This is just attention. No goals. I'm just giving you a foundational concept. Yeah.
So if you go back to your writing, so
Yes.
you did a summation. I think I was lost on the summation when you put the
total attention that the cow has, because it has to pay attention not just to the moon, but to the jump, to all other words.
Okay.
So therefore, it's a summation over all the attentions that it is paying to all the words.
Wouldn't that be one?
No, because those words have certain vector values.
Okay.
So the scores add up to 1, but the moment you take vector values, it becomes a weighted vector. Right? You see, it becomes a weighted vector, and
Just
that
one-
is the
one
gist.
thing on your writings.
Yeah.
Go a little bit above.
Yes.
A little bit further above, I guess.
Okay.
Yeah. So the WI and then like
Yeah.
the WKQK. So I think we started with the EI plus PI, this VI.
Yeah.
That's how we started, but then you changed the WI because of value I.
Yeah, because value. It's just a notation change.
But again, WK times VI.
Oh my God, all of this.
Just
Okay,
one
guys.
clarity,
Yeah. No, this is a good point. I need a new word now for
Yeah.
word. What should we use?
Yeah,
Phi.
token. Maybe
Let's
we
just
can take
use
a token, TI or something.
TI. No, it's not token because it's made out of token.
Yeah, it's made out of token.
Let me
yeah.
just use phi
Oh, okay.
word. Right. The input is phi I. Right. W
Right.
are the matrix.
Uh,
They're capital W. In the
correct.
notation, they're capital
On the
Ws.
right side, WKVI,
Yeah,
The VS,
the value vector, value vector. When you multiply 5 with a WV, you get VI.
oh, okay.
Right? Okay, guys, 1 second, please hold on. I want to give you guys a break and with one sentence. See, guys, look at this. So what happens is every phi I, so now I realize that it's getting confusing. Embedding and position vector makes phi I. Let me use phi because W's also doesn't seem to help. It gets burst out. There are 3 matrices waiting to ambush it, right? And what do the 3 matrices do? They just ambush it and emit out a K, Q, and V, right? So that is this picture. Now what happens? Q and K gets a matrix multiplication. Remember the dot product? Dot product is a matrix operation. Now pay attention here, guys. Do you see that happen? The first Q and K are multiplied. Then they are scaled. Scaled means what is the scaling happening? Yeah, this is the dot product, QK in my notation. This is scaling by minus D, square root of D. Then, I'm asking, forget that. Then you do the softmax of it, softmax operation of this, and then you multiply it by V, isn't it? So they're showing you the graph of operations. Yeah.
Maybe I've missed this thing, but how do we query vector? So just a confusion between the vectors. So cow has a query vector, key vector, and the value vector.
Yeah.
How are they different from each other?
Yeah. See, when cow is asking, who do I pay attention to?
Yeah.
It is paying attention. It is looking up the address of all the other words. Those are the keys.
So when it comes to the vector, like, are they like query vector is made up out of traditional word embedding or sentence embedding logic?
No. Again, let me go back, guys. So pay attention. I'll repeat this. It's important to get it right, guys. See, what the operation is this. This is your word embedding in the sense that you're thinking.
Yeah.
Word embedding. E. That's why I gave it the name E.
Yeah.
Okay. Then I have a position embedding. I concatenate the two, and what do I get? I get this phi I for this word.
That's a new vector.
That's a new vector.
That is a okay.
It's an input vector. Think of it as an input vector. So cow has its own phi cow. Right? Will have its own phi cow, right? Made up of the cow embedding and the cow position.
Yeah.
Then I multiply phi cow with 3 different matrices. WK, WQ, WV.
What are these 3 different matrices? Like the initial, like they're random matrices or what are they?
No. So at the end of it, they're very brightly trained, very well-trained matrices. But in the beginning, you initialize randomly. But the neural network trains them, and they're smart. What they do is they will burst out. They will produce key, query, and values in such a way that cow, when you look at its attention score with the word moon, it will be higher than its attention score with the word the.
But these are fixed matrices.
Fixed matrices. They're learnable matrices. The word you use in neural network is these are learnable matrices that you train a transformer to learn.
But it initially begin with random learning.
It initially, yes, of course, it begins with random initialization.
Sorry, initially the key vector or the query vector are probably empty or with some random values.
No, they'll never be empty. See, even if I take random values for W's,
okay,
they will still project somewhere. They'll just go somewhere wrong. And see, the whole point with neural network is, here's the thing, they're very much like engineers. Have you ever seen an engineer when asked a question, will say, I don't know. They always give an answer, which may be wrong.
That's a good example.
Right? Then you train the engineer and it begins to get right answer. Right? So neural networks are like that. They start out by just say, okay, you want to know, here's an answer. It's just wrong. And then you train and train and train. And then these matrices become smart. Your question?
Very basic question. For your sentence, there are 2 thus.
Yeah.
So the E of each of the the would be the same.
No.
E plus I would be different.
Yeah, EI would be the same. Correct. E plus PI would be different.
Correct.
So phi I
would be different.
Exactly.
But the EI would be the same for both the
Both
thus. So there's no position dependence.
Yeah, because it's just word embedding. Right? Good question. Any more questions? Guys, are you getting it?
So Asif, in a simple world, essentially, we are trying to transform using three different metrics K and Q and V in a way
Yeah.
I can get the attention of each word.
Correctly, exactly. That's what you're doing. Lanki, your question.
The word embedding, sorry, 1 second, sorry.
Hey guys, let's have one conversation. Yeah.
Is the word embedding predetermined? Like,
Generally, what happens is that, so there's a bit of history to it. In the beginning, see, all these technologies were there, word embeddings. Technology existed. You could convert a word into a vector, so that word to word meaning, there's some sense, a good starting point. But nowadays, what people do is, even the word embeddings are learned. Right? So people, I mean, the technology has moved further, but in the original classic picture, just assume that you used a known word embedding technology. Right? Okay, any other questions before I move ahead? Go ahead.
So I thought like when you say two words are close to each other,
Yeah.
that is based on the word embeddings, right?
No, not the word embeddings. There are no word embeddings. Okay. So okay, let's look at this, stare at this picture very carefully. 1 second, Shiv. Pay attention. Word embeddings are EI.
No, I understand.
No, pay attention. Listen to me before you say. EI is the word embedding. I concatenate the position embedding. Even though the cow jumped over the moon, there are two the's. Now phi I of the two the's is completely different. When I multiply them with the W's, they become entirely different keys, queries, and values, right? So that's it. There is no word embedding stops right here. There is no word embedding beyond this.
But why are we expecting that QK and
V,
yeah,
key, query, and value.
yeah, query and value multiplication should be like minimum, right? Like basically, they
Key and query. Why do we expect that it should respect semantics? Like it should understand the language and know that cow needs to pay attention to moon, for example. How do we know that? So who would like to answer this? See, this is the magic of neural networks. We don't. We just say, okay, you know what? We are going to try out the magic of backpropagation and see if we can make this neural network understand the semantics of language such that it produces intelligent query, key, and value vectors with the right alignment. Are we together? So the question that you ask is, as a researcher, is it teachable? Right? Is it teachable? And it turns out it is teachable. Right? That's the magic. That's the magic there.
My observation,
Yeah, go ahead.
the same concept that you said, right, in your quantum science.
Yeah.
Oh, that's given.
Yeah.
It feels at this point, right, something is given to you and I'm not able to grapple it in my head.
Yeah, it is,
And I'm finding it so hard to even like understand, right? We should, get the whole A, Q, B, W, pi, multiply here, there, and finally they all align and then attention force comes.
See, here's the thing. When people make breakthroughs, right? Your point is valid, but when people make breakthroughs, what happens sometimes is they have a certain architecture of thought. These are Google people, so they bring in the information retrieval architecture of thought, and they tried something out. I'll take questions. It worked. It worked beyond anybody's wildest dreams. People have asked that, do we really need this particular architecture of thought, KQV, and to explain why transformers work? And there are actually alternative views. For example, if you look at the writings of researchers like Chris Olah, who I believe is at Anthropic, and a pretty good thinker, he and his team have actually created an alternative formalism of why transformers work that completely avoids this KQV formalism. Right? So it is very interesting that it works. And the people who did it, again, to your point, they come with a worldview. They tried a hypothesis. Just because it works doesn't mean that that is the best explanation. There are other alternative explanations you can come up with.
Alternative models, right?
Alternative explanations of why this works. Right? Interpretations, those are called interpretations for this. And look at the work of Chris Olah, for example. He writes pretty deeply about this topic. If you want, I'll post it to the course portal. They try to come up with a mechanistic interpretation of what really is going on. And they entirely avoid this interpretation altogether. Okay, any other questions, guys? So then I would like to call a break after the last, let it be the last. After that, come to me on one-on-one.
So again, in this example, take the example of the first the.
Yeah.
So it's E0 plus P0.
Yeah.
Phi 0.
Yeah.
Right? It will have an affinity to cow, more than an affinity to jump.
Yeah, it
It
could.
will also have an affinity to move.
Yes, it can. So I'll show you how it works out, guys. Look at this picture.
It can also be the move, the valid. The jump probably is not valid.
Yeah, look at this word, guys. We'll read this sentence carefully. It is in this spirit that a majority of American governments have passed new laws since 2009, making the registration of voting process more difficult. Pretty long statement, right? It takes a while to understand what is being said. It is in this spirit that a majority of American governments have passed new laws since 2009, making the registration of voting process more difficult. They take the example of the word making. What? Making what? Making more difficult. Something more difficult, isn't it? So do you notice that it seems to be paying a lot of attention to the word difficult and more, and making will of course pay attention to itself. And 2009, those things are important, isn't it? In other words, other attentions are not as pronounced. Are we together? So this is the concept of attention. Now you see many stack of bars. Why? That's a multi-head attention part. We'll come to it. But now look at something else also. Look at this other example. See, every word pays attention to every other word. Right? So all of this. Now let me finish it with the multi-attention part, guys. What they realize is this was a very good idea. They had just discovered a new thing, attention head. And of course, after this attention head, what you do is you immediately pass it on to a feed-forward network, standard neural net, feed-forward net. So a feed-forward net, I'll give you a very simple intuition, guys. I call them peanut butter and jelly in a sandwich. So every time you want to put one more layer of bread, what do? You put more peanut butter and jelly. So in neural networks, when you stack things, technologies together, always as a sort of a sponge or as in between, throw in feed-forward networks. You always put those, right? That is why in these networks, I mean, why? Why do they? I mean, I'm joking, but why do you do that? You do that because this is you always pass it through feed-forward. You see this green feed-forward here. After every attention, you try to put a feed-forward. Why feed-forward? What do feed-forwards do? They bring about that distortion. Remember, if it has to be a universal approximator of anything, right? It needs distortion. It needs deformation capabilities. Where do the deformation capabilities come from? From the feed-forward, right? That's why you always throw in that. So now what happened is that when they discovered this, they thought, oh, wow, this thing works, right? And if something works, what do you do with it? You go stacking, you go bonkers with it. So in how many ways can you stack? It's like sandwich, right? One sandwich looks good. What is it? McDonald's did it, right? There's one burger, and then there is a Whopper burger or something like that, right? Double, triple, or something like that. So one sandwich works, put another layer. So they took heads, the output of one, they fed into another attention head and another attention head. So they stacked it n high. It made one tower of attention, right? So input would go in here and bubble out from the top tower. And then they said, well, circuits are there in series and they can be in parallel. Why not create another parallel stack and another parallel stack, right? And so this became multi-head. And what they found is something remarkable. When you create parallel stacks, that's a multi-head part of it. What will happen is one head may be paying more attention to the structure of the sentence. Another may be paying attention more to the grammatical aspect of the sentence. Because in a neural network, what happens is that when you try to minimize cost function and you try to make the machine do the work as best as possible, they behave like human beings. What do? Like if you guys are doing a project, immediately you will differentiate, you'll specialize. One person will say, okay, like in this project, one will say, hey, I know Spark, let me do PySpark, right? Another will say, hey, I'm good at coding, this part, data science, let me do this. Another will say, you know what, I'm good at project management. Let me guide you guys through together with the project. You differentiate. Yeah. Because that's the most efficient way you can bring down the loss. Yeah, you can make the machine. And that's what they found is these machines were doing that. Right? You create this parallel towers, multi-head attention heads, and each attention head would learn something different from the information, but equally relevant. In fact, they will not learn the same thing, because if they learn the same thing, the system is not benefiting. So they will differentiate themselves. And that is the concept of multi-head attention, right? This is all the theory that you have to know. And now what happens is that the encoder will ultimately produce an encoded final attention state. It goes into the decoder, and decoder behaves auto-regressively. Means you trigger it, it produces a word, you feed the word back in to produce the next word in the next word. So that is why this part is a bit auto-regressive. But the encoder is no more auto-regressive. And the best part is that you can feed in an entire sentence and it will come out translated, let's say in French, or it will get a whole paragraph will get translated into a Shakespearean sonnet or a haiku, right? Or whatever you want it to be. Right? And so that is the decoder part, because it produces one word at a time. Decoding is the phase that you see. For example, when you engage with large language models, when you deal with ChatGPT, you see one word at a time getting emitted out. Right? Even though you send in the whole input, one word at a time keeps getting generated out. But when does it stop? How does it stop producing? You keep a magic token in your vocabulary. That token says we are done. Right? So the moment that token comes out, the machine doesn't produce anything anymore. So if it accidentally determines that that's the best token to produce, it produces that and stops. Make sense? That is it. That is it. So guys, this is the transformer architecture. I'll take a break. I'll give you guys a break. The benchmarks. Do we understand? Do you feel you understood much of it?
Little of it for sure.
See, here's the thing. It's a very dense paper. Unless you know the whole background, it's like if you just read the paper, it's a little hard to unpack. I hope I made it a little easier to unpack. And I deliberately skipped a couple of other subtle details. But look at the results. The results were pretty good. And I was going to do another paper, but I think today has been information overload. What's the time?
5 minutes to 4.
5 minutes to 4. So we'll limit ourselves to one paper. Guys, if there's one thing I can tell you for your benefit, if you want to be in this field, most people, they fake knowing things. Right? They talk glibly about it. It's how we survive in our profession. We all have to look smarter than we are. It's a survival thing. So, but this paper, then I request you to really pay attention and read every line of it. After this background, hopefully you'll find it easier to read. I'll post a self-assessment quiz on it, and you can take it and see how much you got. But do that, because this is what the entire architecture of current practices in AI is based on. Everything derives from this. It's important to understand.
Just writing notes will also be uploaded in the portal.
No, the video is there, so you can see my writing. So watch it again. I'll post the video into the portal right away. It's already there on YouTube. If you're on YouTube, you can see it streaming there. And any more questions? Come by to my room. Yeah. Okay. One final question.
Right. Yeah. So maybe I'm going to read this paper, but what is the validation or the authors, right? How did they conclude?
Oh, the proof of the pudding is in the eating. It started beating all the benchmarks hands down.
On the translations or
everything.
Okay.
Just about everything. Out of this came BERT, which I was going to do today, but I'll push it out to next week. But you will see how this thing just lit up the world after some time. Right? So this is it, guys. This is it. I'll end with this. Please use the time to read the project document that I gave, and you can ask me questions. I'll be available. I won't do any more paper reading because this has taken longer than I anticipated. Please do study this paper. It's a seminal paper. I'll end with it.
end as in today's session is ending?
No, this recording is ending,
Oh.
but